Hello, I am Josep Martí from Fabla Barcelona.
I am Teresa Georgallis, a woven textile designer, researcher and educator. And welcome to this masterclass
About how to make your own tools.
on craft practices and digital fabrication.
Digital fabrication is the process where we start with a design in our computer that then we will manufacture in digital fabrication machines.
During this masterclass, we will discuss how to approach digital fabrication to serve the craft sector in a meaningful manner. We will also question how can we ensure the future of heritage craft with the aid of emerging technologies.
The digital fabrication process, it's quite simple. Everything starts with a 3D design or 2D design. Then we will have a CAM process where we will create the files for our machines, and then we'll go to the machines and fabricate our models. Here we can see a big difference between what is CAD and what is CAM. CAD is computer-aided design and CAM is computer-aided manufacturing. So when we talk about digital fabrication, we talk about the mix between those two, because we'll need to have some computer-aided design, so CAD, to design our pieces, to design our models, and then CAM to create the files for the machines. Because for any machine that we will use, any digital fabrication machine, like a 3D printer, a CNC, a laser cutter, a vinyl cutter, for example, we will need to create a file that contains the specific information for the machine to create our own piece. With this concept, we work with what we say from bits to atoms, because we start everything in the digital world with creating like moving bits, ones and zeros, to create our designs, and then we create real objects, so pieces in the real life, like we say atoms in itself. Having this digital process that we transform bits into atoms, we avoid to go into a global supply chain where something is pre-made in China, for example, and then it needs to travel to Europe, the States, or wherever. That it's a long process, and then into here there are many processes that we can doubt on the sustainability of those, because like the piece will be manufactured somewhere, then it will need to travel here. No? Using digital fabrication, we can reduce this process, and it can be the design itself, the one that travels, that is just information that we can send over the internet, for example, and then fabricate it whenever we need to use it. For example, I can design something here in Barcelona, send the files to Berlin, and it can be produced there. When we talk about CAM, computer-aided manufacturing, we have two big families, that is additive manufacturing and subtractive manufacturing. Subtractive manufacturing, it comes when you start from a piece, from a block of material, and you subtract some material from it to create your end shape or object. Additive manufacturing, on the other hand, it's the process where you add material on top of something to create a new piece. There are a lot of differences between them. The main difference here is the use of material. When you have subtractive manufacturing, you always have a lot of waste because you are removing material that you are not using afterwards. Or of course you can recycle, let's say, but for the piece itself, you have to subtract some material that it will be waste. And with additive manufacturing, you don't have this waste because you start with some material and you just create from that material a new thing. So you add material on top of other material, meaning you reduce a lot the amount of waste. Also, there are many differences in the technology itself. Additive manufacturing normally it's way slower than subtractive manufacturing, but we're going to see some examples of different technologies. When we talk about technology, the first technology that comes to mind when we talk about digital fabrication is 3D printing. 3D printing is an additive manufacturing process where you add material to create the 3D printed part. With this technology, we can use a lot of different materials. Really, with FDM, normally we tend to print with plastic, but it's true that there are different technologies of 3D printing that print from ceramics to metals, plastics, resins, many types of materials. But normally when we think about a 3D printer, normally what comes to mind is the FDM printers that print with plastic filaments. But inside this range of plastics, there are many different types that we can use. Depending on the properties we want our piece to have, the properties of the printer itself, we can print many different materials. Those materials can be quite cheap or very expensive, so we have a big range in between. But it's a technology that is quite affordable, so it's cheap to start creating your own designs, to start prototyping. It's a technology that is very versatile and gives you a lot of flexibility on which pieces to create. As I was saying this before, it can create very complex shapes, but the process itself of 3D printing, it's a process that is quite simple, quite easy to start working with it. In this process, the more complex part is the part of the design, because you have to design for the process itself. Because when 3D printing, it's true that you can print almost whatever, but having in account how the machine prints your pieces, you will design it in a way or another to make sure it gets the final object, gets the properties you want. Like the strength, for example, it's true that when you print with layers, it will depend on how you print it. It will have a weak point where it will break, for example. No? So it's important to define in which direction you want to print to make sure your pieces don't break, for example. When it comes to the machine, it's quite simple to set up. To set up the settings, to set up the machine, it's a process that is quite simple and almost anyone can do, let's say. So I would say it's not dangerous at all. It's heating. So it's true that like the only thing it can happen is that you can get burned, let's say, but it's a machine that is quite safe, that you can let it run without having to be there checking that the machine is working okay. So it's a nice machine to start working with digital fabrication. Another advantage of 3D printing is that you don't need much space to 3D print. Really, with the space of the 3D printer, you have enough. You just need the space for the material and the 3D printer itself. It doesn't have any extra components that you will need, so it's a nice tool that you can have on a shelf, for example, and it will not need more infrastructure for it to work. On the other hand, there is a thing with 3D printing, that is that 3D printing is quite slow, let's say. So whenever you want to print something, you will need to spend some time, the machine will spend some time printing the piece for you. Yeah. There are other technologies that are quite faster, like for example the laser or the CNC, where in minutes you can have a working object, let's say. With 3D printing, normally depending on the size of the object, it can go from 1 hour to like days of printing, depending on the size of your print. This is a very simple example. It's just a small piece that will allow you to find the center of a cylinder. But as you can see, it's just a simple piece that it will take around 1 hour to print, more or less. But it's a tool that you can use whenever you are in your workshop. Imagine you need to find the center of a cylinder for any reason, for example, drilling a hole into a pole. You can, if you need to find the tool for this, of course you can go to a hardware store, find a tool for finding the center. But if you don't want to go out to the hardware store, or you don't have the time, or you don't even have like a hardware store nearby, having a 3D printer, you can just design and print it quickly on your 3D printer. Other examples is mold making. There are many ways of doing molds. 3D printing is one of them. For example, for doing slip casting in ceramics, you can create your own custom shapes and 3D print them quite easily on the 3D printer, and then from there create the plaster mold for doing slip casting, for example, or creating a mold directly in 3D printing where you will cast whatever material you want to use, like ceramics, plaster, resins, whatever. So it's a nice technology to create your own tools, to create your own molds, to create your custom shapes that you can use afterwards on your settings. The next technology we'll talk about is laser cutting. Laser cutting is the process where we cut material with a laser, so we will burn our materials. We have a lot of different types of laser cutting machines, but they all work with the same principle, where we have a laser that is a very powerful beam of light that will burn material and will cut through material. When it comes about materials, we can cut a lot of different materials. We can cut from organic materials like wood, cork, cardboard, paper, textiles, you can cut all these types of materials, but also synthetic materials like plastics, for example. There are even laser cutters that will allow us to cut metals, for example. When we're cutting a new material on the laser, the only thing we need to check is that this material can be burned, because when we burn a material, it will create some fumes, and we need to make sure those fumes are not dangerous for us or for the environment. That's why you always need to know which material you're cutting to make sure it doesn't have a safety problem. Laser cutting is a technology that will allow you to cut things very fast, so you can get your results in a matter of minutes. But it's a technology that, as we're burning material, it's a bit more dangerous than 3D printing, for example, because, well, we're burning material, we can create some fires, so it's a technology where you want to stand by the machine and make sure you have everything, all the setup correctly set for the technology. With a laser cutting machine, there is the laser cutting machine that normally it's quite big, but it comes with some add-ons that you will need to add to it. So the space you need for a laser cutting is a bit bigger, let's say. With the laser cutter, normally you also have an extraction, because all those fumes that you create, you want to extract them, for example, extract them outside or even filter them. And also a small compressor. You tend to blow some air onto the piece to make sure it doesn't light up on fire. In the process of laser cutting is a 2D process. Really, what you do is you cut a 2D shape. That, of course, you can have a design where you cut many different 2D shapes and then assemble it into a 3D model, for example. But the process itself is mostly 2D. So in the design part, it's quite simple. It's just designing the pieces that you will cut in 2D, and the laser will follow those vectors. In the cam process is quite simple also, because there are not many settings that you can play with. Normally you have the setting of the power, the setting of the speed, and the setting of the frequency of the laser. That at the end it's how fast the laser is moving, how powerful is this laser, and at which frequency is lighting up the laser. So depending on the material, depending on the thickness of the material, depending on what is the cut you want to do, you will change those parameters to make sure it cuts as you want. With the laser, we can cut, but also we can engrave. So it's a tool not only for cutting, but also we can engrave onto the material. For example, we can mark some lines, we can even draw pictures, we can even engrave them on the materials. So it's a versatile technology that will allow us to cut pieces, but also mark those pieces. So, for example, you can cut a ruler where you can engrave all the numbers and all the lines, divisions, and cut the outer part with just the laser. For creating your own tools, the laser is very useful because it allows you to create tools very quickly, very fast, with materials that are solid enough, like wood or acrylic, for example, that will allow you to create some tools that you will use in your day-to-day in the workshop or in your design process. First thing it comes to mind are stencils. You can create a lot of stencils for painting. You can create stamps, for example. That stamps you can create in many different materials like epofoam, wood, even cardboard, rubbers that are like more professional stamps, let's say. Or even acrylic, because you can stamp with ink, or you can even, for example, following the example of ceramics, if you have a ceramic pot, you can create a stamp to put your logo, for example, and create it with acrylic or wood, where having the clay not dry, not completely dry, you can just stamp it with your own logo. Another very simple example is this router guide that will allow you to create a center point in a piece of wood, for example, and then do a perfect circle with a router, where you just pin the center of pin this piece on the center of the circle you want to create, and then attach the router onto it. Like this, there are many tools that you can create in a matter of minutes, that will allow you to find a center of something, to define the distance between two pieces, to hold two different pieces together to afterwards cut them. Day-to-day tools that, of course, those tools for sure you can buy them in a hardware store, but you can always create your own tools and use them as you like. Another nice example is an example that you will see in another DD masterclass video. That is an example of a loom that is completely laser cutted. So you can just laser cut your pieces to create a loom that afterwards you can use for education, you can use for your own use, for creating your own textiles, for the end as a normal loom. Then the next technology we're going to talk about is vinyl cutting. Vinyl cutting is similar to the laser cutting, let's say, because it's a process that is subtractive like laser, needs in 2D, so it cuts 2D shapes. But in this case, the big difference is that it's not burning the material, but it's cutting it with a knife. In comparison with the laser, the vinyl cutter, it allows us to cut much thinner materials, but it doesn't burn those materials. So we don't have this danger of burning a material that will release some fumes. It's just cutting it with a knife. So it's a technology that is much safer than a laser cutting machine, for example. It's true that we have more limitations because the thickness that we will be able to cut is much thinner. And there are also other materials that maybe we cannot cut in the vinyl, like some textiles. When are very flimsy textiles, we will not be able to cut them in the vinyl, but yes, on the laser, because we just lay them on the laser and it will burn it. With the vinyl, as the knife will drive along the material, it can move it and it can end up having a messy cut, let's say. As I was saying, it's a 2D process, so all the cut part, all the design is in 2D, that you can design with vectors, so the machine will follow those vectors. With the vinyl, we have a knife. It's true that we can change the tool, so we have different types of knife. We can even put a pen or a pencil, so we can also draw on the design before cutting it. Just with the knife, you can cut all the way through, or you can make a marking with the knife, so afterwards it can be a bending point, for example. Where you're working with a cardboard, you can just cut a line, not cutting all the way through, so in that point you will be able to fold it. This technology, it's fast, it's cheap, and you can use a wide range of materials, coming from papers to vinyls, of course, to some fabrics, some thicker cardboards, even some thin woods. So in this case, there are many materials, and many materials that you have laying around in our day-to-day. Like a 3D printer, a vinyl cutter, it doesn't need anything else more than the machine itself and a couple of tools like tweezers to afterwards process your object. But it doesn't need an extraction, it doesn't need anything else, just the machine and the plug. Using the vinyl cutter for creating your own tools, it's very useful when you want to create, for example, labels. If you want to create vinyl stickers that you will label around your workshop, for example. When you want to create thin stencils, for example, for afterwards painting, or even marking designs, creating, of course, stickers that can go anywhere. Here you have an example of cutting a stencil with the vinyl cutter that afterwards it will be used for etching glass. So it will be laid in a glass cup. Then with etching paste, you can etch this glass, so you will have like a marking on this glass. This, you can also do it in the laser, but it's true that with the laser, as the glass itself, it's cylindric, just with a XYZ normal laser cutting, you cannot do it perfectly because you should rotate the object to make sure the focus is always on the same spot. And also, etching glass on the laser is not the safest thing, let's say, because it's easy to break the glass. There are of course options, but like this, it's very fast and effective way of doing it. Our last example is what we call CNC, really the CNC milling machine, where we will be able to cut much bigger pieces. When we talk about a CNC, we imagine a big CNC. It's true, there are also smaller CNCs. And let's talk about big format CNC, where we can cut bigger pieces, bigger materials, and have bigger final objects, because for the other technologies we talked about, for example 3D printing or with vinyl, we are more limited in the aspect of size. With the CNC normally we can go quite big. CNC milling is a subtractive manufacturing process because you start with a block of material, let's say wood for example, and from there you mill your end piece. When you're milling, you kind of destroy this material because it will destroy it in small pieces, in these chips. This process can be 2D like the laser or the binding, but it can also be 3D. So you can put a big block of material and mill it, like for example in a sculpture. It has some limitations depending on the machine itself. When we talk about CNC, normally we imagine a 3-axis CNC where we have X, Y, and Z. So normally when we're milling, we have the end mill coming from the top, and we'll have this limitation. Yeah, we cannot mill underneath. Yes, we can of course flip the material itself to mill it from different sides and have a 3D object itself. But just milling from the top, we can end up having 3D objects just with the single CNC. We can cut a wide range of materials like woods, plastics, metals, many different materials that we can cut on the CNC. We don't have the problem of the laser that it's burning. In this case, we are not burning, so it's completely safe to cut those materials. And it will give us the flexibility of choosing those materials and even work with different materials at the same time. So we cut different pieces that afterwards can assemble together into the final piece. When it comes to CNC milling, we need a big infrastructure because normally the machine is quite big and it's messy because it creates a lot of dust and excess material that we will need to clean. So it's not like a 3D printer or a vinyl cutter that you can have it on a shelf. It's something that you want to have it in a space dedicated for the machine because you will need to clean it a lot during the process. With CNC milling, the cut and the cam process can be very complex. When it comes to cut, it can be very simple, like just a 2D drawing like in the laser or in the vinyl. But of course, if you want to mill in 3D, you can, so you will need to have the 3D model. And when it comes to cam, it's when it gets more complicated because the settings for all the machine, there are many settings that you can decide, and it's not as straightforward as the other types of technologies. Also, with the CNC milling machine, you have the machine itself, but then you have the milling bits that, depending on the material you want to cut, depending on the shapes you want to have to your objects, you will need to decide which milling bits you want to use. The CNC is very useful for creating your own tools because it gives you this flexibility of creating big things, but very customizable. In this case, a nice example is OpenDesk, that is an open repository of CNC furniture, where from flat panels of wood, you can create your own furnitures. They give you the designs, and you can just create the cam and load it to your machines. Or a nice example of a student from Fabla Barcelona from the Fab Academy course that they developed in the CNC. They created a vacuum forming machine. Cutting a panel of recycled plastic, they created a vacuum forming machine that allow afterwards them to vacuum form some leather into the final shape. Now that we had a quick review of different technologies that we can use inside digital fabrication for creating your own tools, it's important to understand why you want to create your own tools and why you don't go directly and buy them somewhere or in the internet, for example. If you build your own tools, really the only thing you need is like the material you want to make it with and the machine itself. Then you will decide how you create your own tools. This, in terms of sustainability, it's quite obvious how you just have the material and you create it yourself instead of having to order it online that will come from somewhere on the world and it will need to travel to your workshop to use it. So it's always more sustainable to create your own tools. Also, it gives you a lot of flexibility. You can create your custom parts. So maybe you don't find exactly the part you want on the market. So creating your own tools, you can customize it to your own designs, to your own sizes, to your own works. So it's a nice tool that will give you a lot of flexibility. Also, it allows you to prototype quite easily and quite fast. So if you are in the process of trying new things with digital fabrication, you can create a tool that afterwards you can adjust and create a new one. So you can always keep improving those tools. If, on the other hand, you just go and buy an already made tool, you will have that tool, but whenever you need another one, you will need to buy a new tool. No? With this, you can create these adjustments on your tools and create the tools that you really need. We talked a lot about creating tools, but there is a very thin line between creating tools and creating machines that you can also do with digital fabrication. Because of course you can create a small tool for your workshop, but you can create a tool for a machine that will allow you to do something else. A nice example is the paste extruder that we developed here in FabLab Barcelona, where from a 3D printer, with that 3D printer, we can print all the pieces needed to create a paste printer that really will adapt the extruder of the 3D printer into a new extruder for paste extruding. So you can connect, you can print with clay, with any paste material, biomaterials, like any paste material. So really, it's creating a tool for the machine to be a new machine. This is a nice example of why digital fabrication gives you this flexibility and expands the limits of your tools. But there are many examples of machines done with digital fabrication. Like a good example is RepRap. RepRap is the project of how a 3D printer can print another 3D printer. So it's how you can print the pieces for a new 3D printer with a 3D printer. So it's a machine that makes a machine that makes a machine that makes a machine. So it's an infinite loop. We also have an example of precious plastics that are machines that you can build using the digital fabrication in the lab to afterwards recycle some plastic. So it's creating a machine that is also a tool, because it's a tool that you use to recycle plastic, for example. There is the concept of Fab Labs 2.0, that are Fab Labs created in Fab Labs, so our machines creating other machines to create a new Fab Lab. So it's this process of how from one Fab Lab you can create the same machines that are on that Fab Lab. You can create those similar machines with only the digital fabrication machines. Yeah. So from one machine, create new ones. So it's also replicating the technology, like the RepRap process, but bigger scale with a whole Fab Lab. Also here in FabLab Barcelona, we developed the six-pack milling machine. That is this small educational machine, that it's a machine completely done with digital fabrication tools. In fact, there are different versions, one created with the laser, one created with the 3D printer, and some custom electronics that will allow you to build a small CNC machine. So really, it's using digital fabrication tools, allows you to create a machine itself, that we use it for education, for people to learn how a CNC works, to assemble it, know all the process involved into building a machine, and knowing the limits and how to use those machines. So it's a nice educational tool also, using digital fabrication to create the tools for having these educational kits. We talked a lot about how you design your own tools and how you create your own tools, but the part of design your own tools, it's not really needed if you don't have this design skill, because there is many people using these digital fabrication tools. So there are a lot of repositories of open source projects of tools that people developed already that are available for you to just download the file and print it on the 3D printer or cut it in the laser cutting. So it's important to understand that, of course, you can design your own tools, but if you don't have this design background or these design skills, you can always use the digital fabrication tools to create tools that someone else already created before.
My practice spans across handmade processes, textile manufacturing, and material research. But first and foremost, I am a maker and a hands-on designer who truly values having direct contact with tools and materials. In 2020, I co-founded Threading Stories. This venture began as a research project investigating Latin American craft practices and their invaluable contribution to the making communities around the world. The investigation between maker and artifact led into an in-depth observation of traditional practices and cultural association. The research focused on inherited knowledge transmitted within objects, investigating symbols, messages, and clues embedded within artifacts. On many occasions, traditional craft reflects a distinctive worldview in an attempt to articulate a diverse understanding of life. Through the research, it was and still is evident that craft practices bear a unique historical and cultural value, undoubtedly worthy of preservation. Now, Threading Stories, as it currently stands, is a design studio that celebrates craft, processes and materials. It is a platform that acts as a resource site, an educational space and a store, presenting artworks that range in scale, shape, material and color. The purpose of this session is to emphasize the significance and benefits of adopting a multifaceted working approach that fosters collaboration, encourages transdisciplinary practices, and facilitates an interplay between different industries. Our primary focus will be on the intersection of digital fabrication and traditional craftsmanship, and how our working methods and tools can serve as a bridge between these two design-make fields. The session will commence with a brief research presentation that establishes the connection between makers and emerging technologies, laying the groundwork for our discussion. Following on, we will delve into a case study featuring the FL project, which will build upon the framework introduced at the start of the session. Finally, we will conclude our session and wrap it up with the exercise that can be completely customized to fit any discipline. Now let's begin with the theoretical part of the masterclass, where we will be analyzing the craft sector. The craft sector is undergoing a transformation as a driver for sustainable development. When we discuss craftsmanship, it often evokes concepts related to cultural significance, heritage preservation, material awareness, and the exchange of knowledge across generations. The current craft revival is a predicted movement, in my opinion, directing towards alternative and sustainable progress. Handmade processes, traditional techniques, and ancestral practices encourage a thoughtful interaction with our environment, but with ourselves. However, the complexity of craft practices and the lack of economic data within the sector has resulted in underinvestment of innovation and education when compared with the rapid growth of interlinked industries. What is suggested here through the FL project, which we'll present later, is a shift of direction and a proposal for a multi-layered working pattern that presents collaboration, transdisciplinary practices, and a symbiosis of industries. Now let's direct our focus towards emerging technologies and how they might contribute to the preservation of traditional craftsmanship. Digital fabrication occupies a unique position in the domain of artifact creation, sitting somewhere in between traditional, small-scale craftsmanship and the mass production methods of industry. Imagine a spectrum with artisanal craftsmanship at one extreme, digital fabrication in the center, and large-scale industrial production at the other end. Now, in this context, digital fabrication is commonly located within fabrication labs and maker spaces, accessible to designers, makers, and the wider creative community. As we explore the synergy between rapid prototyping and creativity, it becomes evident that fabrication technology can serve as a valuable ally to the creative process, nurturing collaborative design and production. The following question arises: can we cultivate an interdependent relationship between craftsmanship and digital fabrication, with craftsmanship taking the lead and digital fabrication complementing and facilitating the design journey. In order to identify a common ground in craft and digital fabrication, we need to dissect both workflows. Digital fabrication commences with the conceptualization of a design, often realized through 3D modeling or programming, and concludes in the sometimes precise fabrication of the predetermined design. This production entails that the design is fully conceived before the manufacturing phase begins, carving a clear path for the exact reproduction of the object or the artifact. Craft practices begin with the inception of an idea, utilizing various methods like hand drawing, digital sketching, material manipulation, and many more. The next phase involves the selection and experimentation with materials and techniques before advancing to the production's final stage. During this ultimate fabrication stage, a dynamic interplay unfolds between the material and the maker, resulting in the creation of a one-of-a-kind artifact. The craft process is characterized by an inherent interdependence where materials and artisans may seem to operate autonomously, yet their interactions and interdependence ultimately bring them together. When it comes to rapid prototyping, we notice a missed opportunity: the potential for both material and the crafting process itself to influence and shape the final outcome. Similarly, in traditional craft practices, there's room for improvement in terms of streamlining the production process, allowing more time for creativity and minimizing the need for corrections. In summary, what if we incorporated elements of improvisation, material responsiveness, and real-time decision-making into fabrication technologies? And what if we could enhance or develop new tools and processes to support our craft making and creation? Merging digital technologies and craft skills allows makers to explore a transition phase between the two settings. In this instance, the design process is led by traditional practices and assisted by technological developments. The project, the FL project, presents a design journey informed by a highly specialized craft and resulting in a product designed and produced by fabrication machines. Understanding craft as a master skill and recognizing technology as a useful tool presents possibilities that propel craftspeople, designers, and makers into new territories and suggest a symbiotic and collaborative working relationship. The nature of weaving somehow allows the blend of the traditional and the emerging to harmoniously come together. Weaving entails material manipulation, mathematical formulas, sequential repetitions, and multi-scale geometries. It is an art form that can transform into a symbolic and collective practice, formulating networks within communities and cultures. Woven cloth mechanism can incorporate actions of winding, locking, and layering, with an overall systematic motion for composing a textile. Similarly, digital fabrication techniques feature an analogous action range with comparative construction methods. In addition, the design, planning, and calculation of a woven pattern uses a binary writing system to record the countless variations of repetition, once again creating a bridge between the analog and the digital. Recognizing the shared aspects in the production process of digital fabrication machines and traditional craft tools opens up possibilities for envisioning a future in which these tools and methods can seamlessly interact. This establishes a connection that transcends the individual creator, instead emphasizing on the inherent qualities of materials and tools. Before we proceed to our case study, let's address the fundamental problem this project aims to tackle. Why did we set out to innovate a tool that has perfectly served the sector for decades? Weaving is a globally practiced discipline spanning from household settings to professional design studios. It ranges from a simple layout of 4 sticks of wood, known as the backstrap loom, to a highly automated dobby loom. The focal point of this project was to examine table looms, typically used in education, design studios, and by weaving enthusiasts. Our goal was to develop a tool that is space efficient, accessible, ergonomic, and portable, with a crucial emphasis on local production capabilities. We believe that in the current climate, where universities, studios, and educational institutions are often reducing workshop space, we believe that altering our tools is imperative to ensure the continuity of our craft and to potentially facilitate the reintroduction of craft practices at all levels of education. Moving on to our case study, as I mentioned earlier, I will present to you the FL project. The foldable loom project suggests a cooperative relationship between makers and emerging technologies. It is a product developed by textile professionals in digital fabrication labs, recreating a loom that is portable, accessible, and complex enough to serve the textile industry. Here I would like to highlight the significance of having a craft practitioner, such as a textile professional, to take the lead in experimenting with their craft tools. The insights, feedback, and deep understanding of a maker can greatly enrich the development of a prototype and ensure it aligns with the current needs of the craft. The project objective is to introduce an educational design-make tool that promotes and preserves cultural heritage, whilst exhibiting a successful example of innovation and tradition deriving from interdisciplinary exchange. The project was divided into 3 key stages of research and development, working with interactive prototyping. The initial phase centered on the creation and construction of a model using 3D software. The model established the design framework and optimized the manufacturing process, therefore minimizing waste, reducing costs, and streamlining timelines. Following on, the project transitioned into the testing and evaluation phase, where the prototype was assembled and thoroughly examined for usability and functionality. Finally, the work underwent meticulous revision and refinement before proceeding to the final stage of manufacturing, producing a series of functional prototypes. The production of the foldable loom required numerous skill sets, from 3D design to textile manufacturing. The prototypes were developed in makerspaces, fabrication labs, and textile studios, with the final assembly taking place in wood workshops. The entire process presents the complexity of designing a refined product that uses local infrastructure and combines processes and expertise. Here I listed some of the materials and tools, as well as expertise, that were required to produce this prototype, to emphasize the process for designing and making such a tool that can have an impact for professional weavers of all levels. The foldable loom project has resulted in the creation of an educational design tool that both promotes and preserves cultural heritage and traditional craft practices. This product is tailored for use in arts education, with the dual aim of nurturing traditional craftsmanship and providing a versatile tool for designers, makers, students, and industry professionals. Our objective was to develop an easily accessible product suitable for operation in diverse settings such as workshops, design studios, and educational institutions. The final product showcases the application of various digital fabrication technologies and really highlights the potential for small-scale production runs. Ultimately, the project sought to demonstrate a successful amalgamation of innovation and tradition, emphasizing once again on the significance of interdisciplinary knowledge exchange. To recap and wrap up our discussion, let's revisit our initial questions. How do we approach digital fabrication to serve the craft sector in a meaningful manner? How can we ensure the future of heritage craft with the aid of emerging technologies? In my view, the solution lies in embracing experimentation and adopting a trial and error approach. Every discipline has its unique attributes, operates within distinct parameters, and engages with diverse materials. As we explore the fusion of digital fabrication and craft, it becomes evident that the design process should be primarily led by traditional practices and assisted by technological developments. Furthermore, it is essential to acknowledge craftsmanship as a master skill and technology as a useful tool. This approach essentially reverses the current roles and fosters a dynamic interplay where both disciplines are equal and interdependent, facilitating progress and innovation. To conclude our discussion, I invite you to engage in a disruptive workflow exercise. Let's collaboratively identify a challenge within your practice. Using a straightforward diagram, select a product, an idea, a service, or a practice, and begin by filling in the timeline, starting from the concept or idea and concluding with the final fabrication or formulation of whatever you wish to explore. As an example, I have created a timeline for the FL project, identifying the need, the point of a workflow disruption, the tests and trials, and finally, the fabrication results. During this exercise, reflect and explore, experiment, and rediscover stages within your practice that could benefit from enhancement. Can you identify a missing tool, a problematic process, or an obsolete working methodology? Moreover, think about how emerging technologies could accompany you during both the design and the making stages of the practice. Where can these technologies play a supportive role in your creative and manufacturing process? I hope you enjoyed this masterclass and found it both inspiring and valuable for your practice. Thank you very much for spending this time with me, and I wish you all a creative journey.